Good morning. I hope the sound is on. Yep, good morning. It's Sunday, which makes a change. Sunday, the 12th of July, and this is Physics for Keith, my scheduled physics revision session, tutorial session for anyone out there on the internet that wants a bit of help. I see we had 3 people watching the stream live. It's gone down to 1 again. That I think is me, so I think everyone might have disappeared now, or maybe the live counter stopped working on YouTube. Maybe I'm just here talking to myself. I didn't get any questions come through this week, or any topics anyone wanted to look at, so I guess that meant it was dealer's choice. And I chose to go for lenses because it's something that students sometimes avoid because they find it difficult, which is absolutely the wrong approach to take. If you find something difficult, you should do more of it. In fact, that's where the fun lies, is doing things that you can't do. No point doing things you can do, you don't get anything from it. So I thought we'd have a little look at lenses today and see how we get on. If you're out there thinking, is this on my course? It's on the IGCSE, the EdXL IGCSE has a little bit of lenses, I think, or at least it used to. The Cambridge IGCSE had a lot of lenses and curved reflectors as well, which are very similar to lenses. It is now on the new 9:1 GCSEs as well. You'll find you'll need to do concave and convex lenses there. And if you're studying A-level physics and you're doing astronomy, and I think it might even be part of medical physics, can't remember, then lenses appears there as well. So this does appear in a few places across the course, and it's a fundamental idea in geometric optics. In fact, it uses fundamental ideas in geometric optics. Geometric optics refers to optics is to do with light and how light behaves when it encounters materials, and geometric optics is so named because the majority of what you're doing, you're solving just using geometry. And maybe this is why students don't like it so much. They learn geometry in mathematics, learn about triangles and straight lines and all this sort of thing in mathematics, and then when they walk into a physics lesson they forget it all. And this is something I commonly see. This isn't a criticism, this is just what happens. Students learn how to take gradients in maths, then walk into a physics lesson and don't know how to take gradients, or they know how to rearrange an equation to find x in maths, and they walk into a physics equation, we ask them to find t, and they can't do it. So geometry appears quite heavily in lots of areas of physics, and students don't like it. They find it difficult. So let's see who we've got. I've got a little message here saying that Teddy's online. That's good. That's one person. I wonder if any of my other regulars are online right now. If you could drop me a little message. This is live, so as we go through this, if there are any questions you want to ask, you can pop your message onto YouTube straight into the chat, or into Facebook Messenger. I have had a message this morning about a topic. I haven't looked at it yet. Somebody sent me a little video and asked me to have a look at it maybe next week, so I'll have a look at that over the week, and then I can do something about that next week. So I'm not ignoring you. I've seen the message. I just didn't really have time to look at it properly, watch the video, or respond to it. And if you have any, if I ask any questions during this, please feel free to go ahead and answer them. Now, in this session, it'd be quite good if you had a pencil and a ruler, and I mean a protractor or a set square would be good to draw 90 degrees as well, because as I go through some problems with lenses, it would be quite nice if you could go along, do them at home as well, and see what your answers come out as, and then we can compare them to the answers that I have here. So let's start with the basics of lenses. Then I've got a lovely little simulation that you can get to show you, and then we'll ask you some questions. So let's start with the very first idea in lenses, which is the idea of refraction. So do you know what refraction is out there in internet land? Have you ever heard of this thing called refraction? Let's just write down the spelling of it in case you're thinking you may have heard of it, but it sounds like some often confused words. So and I've spelt it wrong. Refraction. Not to be confused with diffraction or reflection. Refraction. Okay, so no responses yet. Refraction is a phenomenon where light slows down as it enters a medium. The reason for that is very, very complicated. It's to do with coupling electric fields, and it really goes beyond A level. And I often like to tease my A level students a bit by asking them why light slows down when it enters glass, watching them come up with some fabulous answers, none of which are right, and they do find that quite frustrating. But as a general idea, as light enters something, a medium which is more dense, for example, here I've got a piece of glass in the middle, and here I've got a ray of light entering it, the light will slow down. And as it slows down, it's going to change direction. So the normal ray of light would go straight through the glass like this. But because the light is slowed down, it refracts, which is a technical name for that slowing down of light, which causes the ray to change direction, bending it a little bit. And as the ray leaves the glass, it speeds up again, which means that rather than following the path it was going through in the glass, it follows the path in the same trajectory as it entered the glass. So it's sort of this thing here. Hopefully I've drawn that okay. And the reason why we have the ray changing direction when it slows down is to do with geometry. And I won't go through the proof of that now, but I've got a rather nice, it's not a PowerPoint, I don't like PowerPoints, it's a PDF presentation where I go through the derivation of what we call Snell's law. So if you're interested, look up Snell's law and the derivation of it, and you'll see that this all falls out of the geometry of a situation where light slows down when it enters a more dense medium, and speeds up when it enters a less dense medium. The word medium is just a technical term that means stuff, the stuff through which the light moves. Now I've added two grey lines here. These two grey lines are 90 degrees to the surface of the block. And we call those normals. The word normal in physics means 90 degrees. So those two lines, they're just construction lines. I've just drawn them to help me complete a diagram. They're not sort of lines in space that are really there, and I could have drawn these normals anywhere. I've chosen to draw them where the ray, this ray of light, enters this glass block. And what you'll notice is that the angle of this ray is bigger than the angle of this ray, because the ray has been bent towards that normal at that first interface, at this interface here on the left. Now we call the ray that comes into an interface the ray of incidence, or the incident ray, and the ray that leaves that interface as a refracted ray, or sometimes a transmitted ray. And so we call the angle that the incident ray makes to the normal the angle of incidence. And we call the angle that the refracted ray makes to the normal the angle of refraction. Then you can see that as the ray enters the glass, or this could be any more dense medium, the angle of incidence is larger than the angle of refraction. And there's a beautiful equation to explain that, which I might include a little bit later, which we use at A. Okay. Are we back online? Someone could drop me a little message there. It looks like OBS, my encoder, just conked out for no reason that I can understand. I think we're back online. I think everything's okay again. But it did just conk out, and it looks as well like... Yes, it looks like OneNote has conked out as well, so I'll need to restart that. Sorry, ladies and gentlemen, technical difficulties. These things sometimes do happen, but I think we're rolling again. Right, that's saying that it can't see the display. So, properties. Yes, I think I'm going to have to restart my encoder. So, I'm apologising for this. Stand by. We're about to lose the feed. I think we're back online. I'll double check my stream. Yep, I think we're back online. Right, my apologies for that, but we have our feedback and we're good to go again. That is the first time that has happened to such a catastrophic way. But there we go. Technology, ladies and gentlemen. Good fun. It doesn't always do what you want it to do. So hopefully I'm back online. There's a second interface here, a second place where we change medium. That's what we mean by the word interface. And that's here. That is where the light ray leaves the glass. And you can see the angle here is smaller than the angle here. We call the ray that enters this interface the incident ray. So the thing that was the refracted ray becomes the incident ray and then becomes the refracted ray when it leaves again. You can see the angle of refraction is now bigger than the angle of incidence. So if we are entering a more dense medium, our angle of refraction is less than our angle of incidence. And if we are leaving a more dense medium or entering a less dense medium, then our angle of refraction is bigger than our angle of incidence. We refract away from the normal. So what does this have to do with lenses? Well, let's take a very simple example. Let's imagine that we have a piece or three pieces of glass. A triangular piece of glass at the top, a triangular piece of glass at the bottom, and a rectangular piece of glass in the middle, betwixt the two. Now, if we picture three rays entering this glass, and this is where we're going to have some questions now, so I'm going to want you to using your best sort of scientific language, tell me what you think happens. We have a ray entering here. Let's have a ray entering here, and let's have a ray entering right in the middle here. Let's start with the ray that enters in the middle. What do you think happens next? Where do you think that ray goes? I had a message just go through on the Facebook chats. No, sorry, in the YouTube chat saying, is this similar to what happens when you put an arrow behind a glass of water? Very, very similar to that, yes. And actually, you'll understand that phenomenon when we finish going through lenses. You'll understand why you see the arrow appear to change direction. So you'll be able to, and actually you'll be able to make measurements from that arrow to find properties of the water, but we'll do that later. So what do you think happens to that middle ray? Let's number these ray 1, ray 2, and ray 3. So what do you think happens to ray number 2? Goes straight through. Absolutely right. It goes straight through, undeflected. And I'm just going to draw this all the way over here because it carries on forever and ever and ever. So there we have our ray. We'll draw arrows to indicate the direction of the ray, passing straight through the medium undeflected. It does slow down in the glass, so whether or not it refracts depends on your definition of refraction, and frustratingly different exam boards define it different ways. If you, I think AQA says it doesn't refract because it doesn't change direction, whereas I think CIE GCSE, the IGCSE, says it does refract because it slows down. This is the nature of physics, I guess, is people disagree. Okay, so what happens at this top interface? What happens to this ray? It's entering this glass. Is it going to go straight? Is it going to be deflected? If it is deflected at that first interface, which direction is it deflected? What do you think? I'll give you a little clue. I'm going to add my normal to this glass. Well, I'll do the best to add my normal to this glass, which is 90 degrees to the surface, which is about there. So, deflects down. Yes, it's going to refract towards the normal. That will deflect the ray downwards a bit. So now we're going to be deflected downwards a bit, and I might exaggerate this. Now what happens at the second interface at the top? And I'll draw a little normal, see if that helps you. So we're deflected towards the normal, which caused it to deflect downwards a bit. Now we've got our second, oh dear, that's nowhere near where I wanted it to draw. Let's move this. La, 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 la. What happens at the second interface? What do you think? Is the ray going to go straight, or is it going to be deflected? And if it's deflected, is it towards? Upwards. I see why you might think that, because you deflect downwards entering the glass, upwards when you come out. But no, because of the shape of the glass, that's not what happens. Let's look at each of these normals in turn. So, and I'll zoom in here so you can see it a little bit more clearly. This is another advantage of doing things with a virtual whiteboard. Here, at this, let's get my hand cursor out, move across. Here, at this interface, the red ray is refracted towards the normal, which is why it seems to bend down a bit, deflects downwards. Now when that ray enters, let's change my cursor, when that ray enters the second interface, so that means it's trying to leave the glass, we can now move the normal from the original one. That's going to be distracting if we have that. Oops, that's, I want its ray to finish going back where it started. There we go. Not that I'm a perfectionist or anything. So what happens now? So we go from glass to air, so we refract away from the normal. Well, the normal now is pointing up over there. It's pointing up here somewhere. So if we refract away from... Come on, start in the same place. If we refract away from the normal, then we are going to end up being deflected downwards because the normal's above it. So away from the normal's deflected downwards. And I hope you can see that with some green arrows. Here, the ray is deflected away from the normal, just as it should be, because we're going from glass to air, just like we said before. And here on the first interface, we're deflected towards the normal, because we're going from air to glass. And in both cases, this beam seems to rotate, on the way I've drawn it on the screen, clockwise. And so because it's deflected clockwise, it's being deflected so that it passes towards this second ray, and it's going to end up going through here somewhere. Okay, so let's zoom out a little bit. And this is just 3 pieces of glass, remember? 3 pieces of glass in these particular shapes. If I scroll up a bit so you can see it. If I then consider ray number 3, that's an exact mirror of a mirror image of what ray number 1 is doing. So ray number 3 is going to deflect, hello, it's gone green. Ray number 3 is going to deflect upwards in the same way as ray number 1 deflects downwards. So that's going to end up somewhere up here. It's got snap to grid turn on. That's why I'm finding it frustrating. And you're going to end up with something looking like this. Now that, if anyone knows anything about lenses, should look a little bit familiar. Because that's sort of what a ray diagram would look like for a lens. Your rays that come in parallel are now focused at a single point, which you can call the focal point. Now, what if I didn't have 3 chunks of glass? I had a continuous piece of glass that curved around. Well, there's a little simulation you can play with. And if you do a search online for PhET, I've mentioned them before, they are good simulations, PhET. And this one is called Geometric Optics. So if you have a search for the Geometric Optics simulator from PhET, you can play around with this, and you've got an object on the left. In this case, it's just a pencil. An object on the right, an image on the right, which is not a real pencil. This is an image of a pencil. And in the middle, we've got this lens, and the lens is a convex lens. That's just the name of this, don't worry too much about it. It just describes the lens that bulges out in the middle. A lenticular lens is called a convex lens. And there are various things we can do with this simulation. We can change the shape of the lens, make it more or less curvy. We can change the size of the lens, the diameter. We can change what the lens is made out of to make it a denser, a heavier glass, or less dense, and see the effect that has on our image. What I'm interested in is how to figure out where the image forms at all. And you'll see there's these two X's marked on this straight line going through the middle. So I'm afraid we're going to have to use some technical language now. I'm not afraid, I like technical language. We're going to have to use some technical language and label some parts of this diagram. The line going straight through the middle we call the principal axis of the lens. These points that are marked with an X are called focal points. And I tend to refer to the one that's on the same side as the object as the near focal point, and the one that's on the other side to the object as the far focal point. The distance between the middle of the lens and the focal point we call the focal length. And it's the same distance on both sides. The whole thing is symmetrical. The distance between the object and the lens we call the object distance. Sometimes we use the letter O, I think, for this. Sometimes we use the letter U for this instead. The distance between the middle of the object and the middle of the lens and the image we call the image distance, and sometimes we use an I for this, and sometimes we use a V for that. Okay, so that's all the bits named. The bit in the middle is a lens. So what happens? Well, I want you to consider, and there should be a clever way of doing this. Can I make a lamp? Is it many rays and screen? There it is, perfect. And let's place this there. Got it, perfect. Right, I want you to consider a light source sending light out in every direction. And if we place that light source dead on at the exact position of the focal point, so it's exactly one focal length away from the lens, what can you tell me about the rays that come out of that lens? What can you tell me about the rays that come out of a lens when the object, in this case it's a lamp, is placed exactly one focal length away from the lens? Tell me about those rays. They're at a 90-degree angle? Yeah, I mean, they don't actually have to be. I could move this up here, I could move this down here. As long as I keep it one focal length away from the... it's about there-ish. As long as I keep it one focal length away from the lens, they still have this same property. So the answer that was written, in case you're not watching the chat, was that they're at a 90-degree angle. Well, they don't have to be, but they are all parallel. All the rays are parallel. And if you remember our diagram we drew, we had parallel rays coming in and focusing at a focus. And here on this little simulation, we've got from a focus and then parallel rays coming out. So this highlights an important property of geometric optics, which is called the reversibility of rays. If a ray would follow a particular path through some optical system, then a ray in exactly the opposite direction would follow the same path but in exactly the opposite direction. That's quite a handy principle. But that's how we define the position of the focal point and how we measure the focal length of a lens. We either get rays that are coming in parallel, and you can do that by having a light source a very, very long way away, and then identify where those rays focus to a point, or you do the opposite. You have some screen over here and you try to produce a spot that's just the same size as the lens when the object with light source is directly on one focal point. Right, now let's move this a bit further away then, as far away as I reasonably can. can you see that when the screen is placed at the point where the rays converge, the image of this source appears as a dot right there? A dot. All the rays come together at that point. Now, if I don't, let's go back to let's get rid of our screen. If I have just an object like a pencil here, that's lost off the side of my screen now. Am I able to get that back? Yes. If I have a pencil here doing the same sort of thing, light is reflecting off this pencil and emitting light in all different directions, reflecting light in different directions, then where this point at the top is, the rays are all spreading out, but they're coming back together again. They're converging at this point. So if I placed a screen here, I would see out on the screen the top of the pencil. That's an image of the top of the pencil. And if I did the same thing from the bottom of the pencil, and this is where it gets complicated, you see, I have loads and loads of rays, myriad rays, infinite number of rays, and they would focus on the bottom of the pencil. And you'll notice that it's flipped, and that's why you mentioned the glass of water. You look at an arrow the other side of a glass of water. This is exactly what's happening. And as I move the pencil towards the lens, what happens to the image? You tell me. What happens to the image as I move the pencil, the object, towards the lens? What happens to the image? Use your best scientific language to describe it. Move the object towards the lens. What happens to the image? No answers coming through just yet. Okay, it's becoming enlarged. Yep, makes the image larger. Good, it's becoming enlarged. The image is also moving further away from the lens. That's the second thing that you'll notice happening. And so conversely, if I move the object further and further away from the lens, the image gets smaller and smaller. But there's a limit. And the smallest the object can be is a dot. And that dot would form on the focal point. And when that dot forms at the focal point, the object would have to be infinitely far away so that the rays are all parallel. And so it's just not physically possible. Now, if I place the object at the focal point, the near focal point, this image would therefore be exactly the opposite. Remember, if I place this object infinitely far away, the image would be a dot on the focal point, the far focal point. So if I put the object on the near focal point, the image would form infinitely far away. It's just symmetrical. It's the same picture but in reverse. This is quite a complicated idea. What it means is the image cannot form because the rays are all parallel to each other. But I can still move the object closer to the lens. So what do you think happens if I move the object closer to the lens? The object is further away from the lens than the focal point. An image does form. The closer I get to the focal point with the object, the further away the image forms, until the image forms infinitely far away. It doesn't form. The rays are all parallel, but I can still move the object closer to the lens. So what happens then? This may surprise you. No answers coming through just yet. Doesn't matter if you're wrong, just have a guess. But as I move the object even closer, the image forms behind it. Now what on earth is happening here? It will form the image, but it forms the image behind it. And if you compare this image to the last one, it's got a few differences. The first difference is that this image is the right way up. It is upright. Sometimes we say it is an erect image or an upright image. The second thing you'll notice is that the image is larger than the object, and it is always larger than the object. I can't make that image smaller than the object. I can make this image smaller than the object or larger than the object depending on where I put it, but I can't make this image smaller than the object. It's just not possible. There's another property of this object which you probably don't realize, you can't appreciate just from this diagram, but it's not really there. This is what we call a virtual image. A bit like looking in a mirror. Exactly right. Yeah, well done. I think it was Teddy that had said that. He said, a bit like looking in a mirror. Yeah, the image that you get when you're looking at a mirror is not real. The light appears to be coming from behind the mirror, but actually it's not. It's coming from your face, reflecting off the mirror, going into your eyes. So these rays, if you followed them back, your brain wouldn't know that they'd been deflected by this piece of glass. Your brain's not that clever, and when it looks, it thinks the rays have come from down here somewhere, and so your brain thinks that's where the object is. Of course, it's not where the object is, it's an image. But what it means is I could place something here, a piece of card, I don't know, it doesn't really matter, something here to block the light, and it wouldn't matter. You'd still see the image behind it. You'd see the image through it. You wouldn't actually see the object. It would look like this is in front of the object that you're blocking it with. So that's interesting, right? But there's too many rays here. We can't draw a diagram with this many rays, and that's where your piece of paper comes in, and your pencil and your ruler, because there are 3 rays that we need to be able to draw that will allow us to construct the position of the image. The first thing we do is we cheat a little bit, and this is all the way through your GCSE. You're always going to place the second point of your object on the principal axis, and that makes it a little bit easier, because now you don't have to track 2 points, so we can get rid of that second point, and we've halved the number of rays I have to draw. That's quite handy. We know the second point is somewhere on the principal axis. No matter where I move this, that second point is always going to be somewhere on the principal axis, and that makes drawing the image far easier. The second cheat we do is we don't try and draw every ray, because there's an infinite number of rays being reflected off the top of this object. So what we do is we choose 3 principal rays, and you have to learn what those 3 principal rays are. And it doesn't matter if the object is bigger than the lens. So if I had a smaller lens like this, we would still draw the same 3 principal rays. You'll notice that all that happens when the lens is bigger is it catches more light and therefore makes the image brighter. It doesn't actually change the properties of the image otherwise. Even though the light doesn't actually follow this bizarre path through air and then spontaneously through air chooses to change direction, we still draw those principal rays because it allows us to locate the position of the image. A very useful thing to do. So it doesn't matter how big the lens is, we still draw these same 3 principal rays. Now let's number them. Let's number them principal ray number 1 on the top, number 2 in the middle, and number 3 on the bottom. Number 2 is the easy one. No matter where I put this object, look at what number 2 does. Principal ray number 2 always passes straight through the middle of the lens and from the top of the object. Always straight through the middle of the lens. So that's an easy principal ray. I can draw that. If I draw a lens and I draw my principal axis and I draw my object, I know there's always going to be a ray. I don't have to number them, but I know there's going to be a ray that goes from the top of the object straight through, so you can see it on the camera, straight through the middle of the lens, where the middle of the lens and the principal axis cross. That's where that ray goes through. And actually, I could even have my object up here. It still follows that same path. Now, this is important to note, that that's only true for thin lenses. Doesn't matter for GCSE level because you'll only deal with thin lenses. Doesn't matter for A level because you'll only deal with thin lenses, although you might have to know a little bit about aberrations. And if you're doing GCSE astronomy, you have to know a little bit more about aberrations that are caused by spherical lenses. And I don't know if you've got any intentions of doing GCSE astronomy out there in internet land. At my school we did used to offer it, but then people realised that the GCSEs were quite difficult. Particularly because we'd just changed to a new style of GCSE, and all of a sudden no one wanted to do an extra GCSE just for the fun of it. And I'm hoping we can pick it back up again as people are settled now into the new GCSE. They're feeling less nervous about it. It's a good course to do, the GCSE astronomy. But no, usually you're only going to deal with thicker lenses and aberrations, which is smudging that's caused by funny things with the lenses. You're only going to encounter them really when you start your degree in physics. It's quite a complicated topic, and that's why we're going to brush over it. Okay, so that's the second principal ray. Now look at the first principal ray and compare it to the third, and you'll notice some symmetry here. The first one is parallel to the principal axis and then refracts through the far focal point. Now, if the image was actually the object, then this ray I'm now tracing with my mouse cursor would be that first principal ray, wouldn't it? Parallel to the principal axis, then through the far focal point. But this isn't the object. This is the image. But it doesn't matter, because if a ray follows the path shown on the top, then a ray in reverse would follow the path in reverse. And so a reverse ray would go through the near focal point and then parallel to the principal axis. And that's exactly what we see with a third principal ray. It goes through the near focal point and then refracts parallel to the principal axis. And again, it doesn't matter where you put your object, you always get the first principal ray through the near focal point. Sorry, they've switched around, haven't they? The first principal ray parallel to the principal axis, then refracting through the far focal point. The second, exactly like how a pinhole camera works. Well, not quite. Similar to how a pinhole camera works. We'll talk about pinhole cameras in a bit, maybe. Yeah, sorry, Teddy asked a question about pinhole cameras. Second principal ray straight through the middle. Third principal ray near focal point and then parallel to the principal axis. And that's it. Those are the three rules. And the nice thing about those three rays is it works even if the object is very far away. If it's exactly twice the focal length away from the lens, that's an important one, because when you're twice the focal length from the lens, your image is the same size as your object. It works when you get right up to the focal point. It actually works when you're at the focal point. Although everything sort of breaks on this simulation, it really struggles. It can't draw this principal ray through the near focal point because you're on the near focal point, so it can't draw it. And these two rays never converge. But you can see they never converge, and that convinces you that no image can form. But it even works when you go with the object closer. Let's just follow those three rays. The first one, parallel to the principal axis through the far focal point, just as we had before. The second one, straight through the centre of the lens, just as we had before. But the third one, which we said goes through the near focal point. Well, why is it coming up here then? Well, if I continued this ray, what would it do? It would go through the near focal point and then parallel to the principal axis. So it obeys the rules, even though the object is too close to the lens. So where's the image form? Well, if I had an eye, the eye of physics, I was looking from this right-hand side, my brain wouldn't know that these rays have been bent by the presence of a lens, so my brain would see these rays coming from a point. And where would they see these rays coming from? Here. That's, my brain knows rays go in straight lines. I've evolved that way. And so I think the object is there. It's called an image. It's not really there. It's called a virtual image. And now you can construct virtual images. Now, I've spent 40 minutes, I'm afraid, spent quite a long time reviewing these convex lenses. And I haven't even looked at concave lenses yet. But I made a question generator. And you've got that paper, and you've got that pencil, and you've got that ruler. So I've made a question generator. I you'll know that I like my question generators, and I'm always happy to share these with anybody that asks for them, anyone that's interested in them. And this one here is my lens drill question generator. And I'm just going to zoom in a little bit so you can see it a bit more clearly. This symbol in the middle is the symbol for a concave lens, and we're not doing those yet. So I'm going to hit F9 to generate a new random question. That's a concave. There's a convex lens. And so we have a convex lens here, and the object labelled with an O on the left is here. And you can see there's the top of the object and there's the bottom of the object. And there are some measurements, but you should be able to read them off the screen because they're on a piece of graph paper. So you should be able to count the squares for this. And what I want you to do is identify where the image is. And the second thing I want you to do is identify how big the image is. And you can do this in squares. We call each of these squares a unit of squares. This is a bad example because the image doesn't form on this one. But I want you to give it a go anyway, and I want you to see if you can draw those rays. Unfortunately, I won't be able to see what you've drawn, but when you've drawn the two, you can't draw 3 principal rays on this example because it's on the focal point, but when you've drawn your 2 principal rays, could you just let me know and I'll show you what it should look like. So you're sketching a diagram, you draw that symbol for the convex lens, you draw your principal axis straight through the middle, you count on the screen and you go 1, 2, 3, 4, 5. 5 squares to the focal point. That's a focal length of 5 squares. So you take your ruler, maybe use one square as 1 centimetre, so 5 centimetres to the left, draw a little X, label it F. 5 centimetres to the right, draw a little X, label it F. Make sure the principal axis is 90 degrees to the lens. Then draw your object. 1, 2, 3, 4 squares up. Label it O. Then you draw your 3 principal rays. Although you can only draw 2 in this example. Then let me know when you've done it. I'll show you what it should look like. I do like spreadsheets. I've made so many of them. The more accurately you draw these diagrams, the more carefully you draw them, the better they will be. It doesn't matter, remember, it doesn't matter how large you draw the lens. On this simulation, the lens is always drawn a little bit bigger than where the principal rays enter it, but it really doesn't matter. You can still use those principal rays. How are you getting on? If anyone's just joining us, because I saw the number of concurrent viewers has just gone up by 1. So if you've just joined us, we have looked at why lenses work to do with refraction. Then we looked at the 3 principal rays for convex lenses. And now I've set a little challenge to draw the ray diagram that you can see on the screen to the left of me here, and to mark on the principal rays. See Teddy's he's just drawing a grid first. Well, you don't really need to draw the grid, but if you find that helps you, that's okay. But you don't really need to draw the grid. You can do it straight onto a piece of plain paper or lined paper. It doesn't really matter. It is easier with a grid though. I don't have any graph paper here. That's all at work. The number of concurrent viewers just dropped by one. So whoever turned up looked and thought, no, I've missed all that. Never mind, and logged back off again. Okay. Well, maybe they'll watch the video back later. Or maybe they are watching the video back, and that's why they don't count as a concurrent viewer. It's possible. Okay, so what I'll do, I'll show you the answers, and then you can have a go at some more questions. So if I click on the Answers tab, it actually shows you each of the principal rays drawn one by one, which I thought was a nice little thing to add. So if we look here, you can see the first, scroll down a bit, you can see the first principal ray, which would go parallel to the principal axis, then through the far focal point, and that you could continue drawing that. It wouldn't matter. The second principal ray is straight through the center of the lens undeflected. The third principal ray is going to be a difficult one to draw. Right now it just draws this and then goes, can't do it. I should really set it up with a little routine that doesn't draw anything on the third principal ray if it's impossible to draw it. But you end up with, I just realised you couldn't see the second ray, could you? Because it's too far over to one side. There we are. That was the second principal ray. Straight through the centre undeflected. And the third principal ray couldn't be drawn. And the answer here. So it says no image forms. The two rays are parallel. And you can see they're parallel. You can see that. So if I now press F9, hopefully you got on okay with that. Do let me know how you got on, or if there are any problems, or if you know anything you think, I got that a bit wrong. Do let me know. So let's go for a different example. Press F9 a few times until I'm happy with one. F9 a few times until I'm happy with one. The problem with random number generators is when you wanted to generate a number you want, it never does. Let's go with this one. Might be a bit of a tricky one to draw, this one. In fact, this one might be a little bit too small for you to draw, but do your best. You might have to scale this one a bit vertically. I think this one's going to be a tricky one. So 2 centimeters to the focal point, 2 centimeters to the focal point, 1, 2, 3, 4, 5, 6 centimeters to the object. Then draw your 3 principal rays. Hey, someone's liked this. That's brilliant. Someone's liked my stream. I'd set up little shortcuts on OBS so I could do things like this. I could put a little subscribe symbol down there to try to encourage people to subscribe. But I really don't get enough viewers for that to be worth doing. No one's watching it, so no one's going to see the message to subscribe, which is a real shame because I need to get to 100 subscribers to change the channel URL. I also put the little advert on the bottom, but I mean that's wrong because it's not Saturday. Does it say Saturday? I do free online tuition. It doesn't even mention Saturday. Fun things you can do with OBS. All skills that we had to learn because of COVID-19. So hopefully you're getting on okay with that. You will get faster and faster as you go through these. So, and if you want to pause the video at any point and then go back, or don't pause it, this live stream will be available for you to watch later. So you can go back and watch these later as well and check your answers. But the answer for this, it's so tiny. I mean, it's coming in at between 2 and 3 fifths of a square tall. Really badly chosen example. But the first principal ray, parallel to the principal axis through the far focal point. Second principal ray, straight through the middle, which you can see here. Third principal ray is straight through the middle, straight through the near focal point, then parallel to the principal axis. When you combine the three together, you get something like that. There's a debug mode built into this, and I can send this to you. Just send me a message on Facebook Messenger. I'm very happy to send this to you. If you switch debug mode on, you can choose your own picture. So, for example, I could choose to put the object here. The only problem with debug mode is it does show you the answer before you even start doing it, so that is a problem. What I can do, however, I can use debug mode off the screen so you can't see it, set you up with a problem, and then oopsie, and then you can see how you get on with it. So let's do that. Let's use debug mode off the screen. Let's give you a problem. So 9. Oh yes, yes, that's a good problem. Oops, no, I've just shown you the answer. So let's have a go at this one then. This is a convex lens. I know it goes right off the end of the screen, but please don't worry too much about that. Your diagram will be fine. So it is a convex lens. Distance to the focal point is 3 centimeters. The object is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 centimeters tall. So you need plenty of space to draw this. But where does the image form? So have a little go at this one. Another advantage of watching this back is that you can play it in a faster speed. 1.5 times is fine. Don't play it at 2 times. You're not going to learn anything from that. Oh, I didn't mention the object is 5 centimeters away from the middle of the lens. But hopefully you can see that on the screen. It's clear enough. Oh, I've got a new subscriber. It worked. Oh, I might put that little subscribe button up again. That's fantastic. That worked. I didn't expect that. Hey, people subscribe to me, please. Oh, that's made my day, that. I wonder if Joe Wicks gets as excited about a single subscriber as I do. Okay, so I'll show you the steps then. So step number 1 was, let's go to the first principal ray. On the left here, parallel to the principal axis through the far focal point, just as we've done before. Then you draw the second principal ray straight through the middle of the lens, undeflected. Then you draw the third principal ray, which is here, which is through the near focal point, then parallel to the principal axis. And then you draw, so you've got all 3 of those together, so you can locate the position of the end of the object, which is, sorry, the position of the end of the image, which is here, and then you can measure how many centimeters that is. So that's what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 centimeters on this little thing here. Wow, I mean, you really did need a big piece of paper to do that. That was bad planning on my part. My apologies for using so much paper. But you'll notice at the bottom here it mentions magnification. Once you can draw the diagram, magnification is straightforward. The image is 1.5 times bigger than the object, so the magnification is 1.5. You just do the image height divided by the object height, and that gives you the magnification. If the magnification is less than 1, the image is smaller than the object. If the magnification is negative, then the image is the same way up as the object, and that happens with those virtual images you saw before. So that's by the by. Okay, so that's convex lenses. I haven't even mentioned concave lenses yet, and we've got another 5 minutes until it's 11 o'clock, so I wonder whether it's worth me talking a little bit about concave lenses. Now, unfortunately, PhET doesn't have a nice simulation for concave lenses, but don't worry, I can draw them. So concave lenses are those... let's just get my tablet, see if you have frozen. Now would be a bad time for my tablet to stop working. I've had all sorts of technical problems today, haven't I? Yep, my tablet stopped working. It's turned into a mouse. So I'm going to have to do this manually. This is not going to be as smooth and as quick, but never mind. A concave lens is one where the edges of the lens curve inwards like this. And so the rays come through. And you've got an idea, if the convex lens deflects the rays inwards, a concave lens deflects the rays outwards. This is me trying to draw with a mouse because my tablet's died again. It is tremendously frustrating, but never mind. So, our concave lens, sorry, the symbol for the concave lens is this. It's much easier to draw than trying to draw the lens. And we've got our principal axis passing straight through the middle. The nice thing about concave lenses is the rules are the same. So if I draw my object, and I'll do this in black. So if I draw my object here, do it like that. And let's draw my focal point there and there. So it's almost the same rules. The second principal ray is exactly the same as the second principal ray for convex lenses. Just go straight through the middle undeflected. No different. But where before the first principal ray went parallel to the principal axis and then through the near focal, sorry, parallel to the principal axis then through the far focal point, the first principal ray now goes parallel to the principal axis and then doesn't go towards the far focal point, it goes away from the near focal point. So imagine where that focal point is and draw the ray passing like that. And what we'd often do is we would, what we would often do is we would use a sort of dotted line here because this is a construction line. The ray isn't really here from this X here. We're just using this near focal point to work out the path of the principal ray. So it's the same and yet somehow exactly the opposite. First principal ray is parallel to the principal axis and then rather than towards the far focal point it's away from the near focal point. So what do you think it will look like for the third principal ray? Now usually exam boards only require you to know 2 principal rays because this one's a bit more complicated. But if you remember with convex lenses, the third principal ray was through the near focal point then parallel to the principal axis. This time it's not through the near focal point, it's through the far focal point and then parallel to the principal axis. And you're going to say, well, hang on a minute, you can't go through the far focal point and then parallel to the... That doesn't make any sense. Well, no, it doesn't. So what you do is you use a dotted line, just as we did before, not there. When you're here, you're using the far focal point to construct the path of the... I don't know why I've drawn this so long, to be honest with you. To construct the path of the ray, but then once it hits the lens, it's refracted, and it refracts parallel to the principal axis. I will move that. Like that. So those are your 3 principal rays now for concave lenses. And where does the image form? The image forms where these rays all converge. So if I do this, obviously this part of the ray isn't really here, It's just another construction line. But can you see that they all converge at that point there? And so our image, which I will draw in, pick a colour, purple will do. Our image will form, move that across a bit, there. So it looks a little bit more complicated, but the rules are the same. And if you can master the rules for convex lenses, then you can use them with a little tweak for concave lenses. And how are you going to remember that? You have to intuitively remember that rays seem to spread out when they pass through a concave lens, but go in towards each other when they pass through a convex lens. And if you look at the symbols, that does rather help, because the symbol that shows the lens itself going out is where the rays go out, and the symbol that shows the edges of the lens going in is where the rays go in. The second principal ray is the same for all lenses, which makes it really easy to remember. That's the one labelled red here. The first principal ray is always parallel to the principal axis, and then it does something. So for convex lenses, parallel to the principal axis, then through the far focal point, would bring it towards that second principal ray. So they'd pinch in, which you know is what happens. But for concave lenses, you want the rays to go outwards, apart from each other, and so away from the near focal point is exactly the opposite to make that happen. And then that third principal ray, actually you don't need. You're only ever assessed on being able to do 2 of them, but I've included it here for completeness. And the way of calculating or way of measuring the magnification is the same. Image height divided by object height is the magnification, although this one would technically be negative because it's the right way up, although you wouldn't be marked down in a GCSE exam for forgetting that. And that's it. So it's 11 o'clock, it's just gone past 11 o'clock. We've had no end of technology problems today. My apologies for that. Someone says, is this like glasses? That was Teddy. Is this like glasses? Yes and no. This depends on the glasses. Some people have prescriptions that are concave, like this. Some people have prescriptions that are convex. I think my daughter has prescriptions that are convex, but my grandmother, my nanny, has lenses that are concave. So I think it depends on what visual defect you're trying to I wouldn't say repair, because you don't repair the defect, but mitigate with the glasses. So you mentioned pinhole camera, and I know I've gone over, but I wonder whether it's worth just talking about pinhole cameras, because they are a very quick section. So you don't need a lens to focus. If I have an aperture, which is a technical name for a hole, then I can get light to focus through that hole. So here we go. Here's something that blocks light. There's a little hole in it. You can just see there's a little hole I've made in that. And let's have an object. And if I have an object over here somewhere, let's say it's a blue arrow, because I'm not very imaginative, then the ray that goes from the top of this blue arrow and yet can be seen on the right hand side must go through that middle part there. There's nowhere else it can go, because all this, the rest of this part of the picture is blocking the light. And the ray that goes from the bottom of this blue arrow has to pass through that hole, if you can see it on the other side over here, and so on and so on and so on. And so if you put a screen at about the same distance away as the object is, let's try and decide what picture. There we are. If we put a screen over here somewhere, well, that's nowhere near the right place, then you can see the bottom of the object will focus here, the top of the object will focus here. If you don't, if you move it closer, then the object will look a bit smaller. If you move it further away, the object will look bigger. So that's how you can use a pinhole camera as a lens. And actually you can do this. If you need glasses, you can sometimes focus by just taking your fingers and putting them very close together and looking at the thing you're trying to focus on, and it may actually help you see things in focus. But that's how a pinhole camera works, so it's not quite the same principle. Right, this is difficult. This is something that year 10s and 11s do struggle with. So if you need to practice this, and of course you do, this little question generator is going to be your friend, because you can just press F9 ad infinitum and get as many questions as you'll ever need to practice these. If you're watching this video back because you weren't watching it live, that's fine. Send me a message on Facebook Messenger, Physics with Keith, and I'm very happy to send this to you so you can get some practice. Otherwise, I intend to keep doing this on Saturdays, this Physics with Keith, but right now I'm looking at over the summer whether it's worth restructuring it to offer a crash course in physics, maybe trying to do the whole of a GCSE or something, trying to do some sort of structured course to help students who maybe have missed out due to COVID-19. A summer school, if you like. Now, if that's you and it's affecting you and you're thinking, yes, desperately yes, then pick the topics that you want to look at, let me know, and I'll see. I'm not going to be able to please everyone, but the more information I have, the more people I can help, and that's what this is all about. We will call it a day there. We've gone on for a little bit too long. Thank you very much for tuning in. Do like and subscribe if you haven't already. Tell your friends, encourage people to get involved with this, because it really works better when people are communicating, and the whole point of this is to make you more confident and better at physics, and I'll do what I can to help you. Okay, I'm going to click stop now. Thank you very much. I'll see you next week on Saturday, back to the usual time and day.